Have you heard from someone about the Monty Hall Paradox? Or ever watched it on somewhere? Every paradox makes us blow our minds. So the Monty Hall Paradox is also like that. Get started to answer the question in the title. What is the Monty Hall Paradox? Story. Before we discuss what is the Monty Hall Paradox, let's together find out the story behind it. The Monty Hall Paradox is named for its similarity to the Let's Make a Deal television game show hosted by Monty Hall. He is one of 3 game show hosts, along with Alex Trebek and Howie Mandel, on both Hollywood's and Canada's Walks of Fame. In the paradox, you are on a game show, being asked to choose between 3 doors. Behind each door, there is either a car or a goat. You choose a door. The host, Monty Hall, picks one of the other doors, which he knows has a goat behind it, and opens it, showing you the goat. You know, by the rules of the game, that Monty will always reveal a goat. Monty then asks whether you would like to switch your choice of door to the other remaining door. Assuming you prefer having a car more than having a goat, do you choose to switch or not to switch? Definition. The Monty Hall Paradox is a famous, seemingly paradoxical problem in conditional probability and reasoning using Bayes' theorem. Information affects your decision that at first glance seems as though it shouldn't. Expand. Almost everyone stays. They figure that since the car was placed behind one of the 3 doors at random and door 3 has been eliminated, there is now a 50-50 chance each that the car will be behind door 1 or door 2. Though there's no harm in switching, they think there's no benefit either, so they stick with their first choice out of inertia, pride, or anticipation that their regret after an unlucky switch would be more intense than their delight after a lucky one. Famous. The Monty Hall Paradox became famous in 1990 when it was presented in the Ask Marilyn column in Parade, a magazine inserted in the Sunday edition of hundreds of American newspapers. The columnist was Marilyn Vos Savant, known at the time as the world's smartest woman because of her entry in the Guinness Book of World Records for the highest score on an intelligence test. Vos Savant wrote that you should switch. The odds of the car being behind door 2 are 2 in 3, compared with 1 in 3 for door 1. The column drew 10,000 letters, 1,000 of them from PhDs, mainly in mathematics and statistics, most of whom said she was wrong. Here are some examples. You blew it, and you blew it big. Since you seem to have difficulty grasping the basic principle at work here, I'll explain. After the host reveals a goat, you now have a 1 in 2 chance of being correct. Whether you change your selection or not, the odds are the same. There is enough mathematical illiteracy in this country, and we don't need the world's highest IQ propagating more. Shame. Scott Smith, PhD, University of Florida. I am sure you will receive many letters on this topic from high school and college students. Perhaps you should keep a few addresses for help with future columns. W. Robert Smith, PhD, Georgia State University. Maybe women look at math problems differently than men. Don Edwards, Sun River, Oregon. Among the objectors was Paul Erdos, 1913 to 1996, the renowned mathematician who was so prolific that many academics boast of their Erdos number, the length of the shortest chain of co-authorships linking them to the great theoretician. But the mansplaining mathematicians were wrong, and the world's smartest woman was right. You should switch. If you do not switch, you have the expected 1/3 chance of winning the car, since no matter whether you initially pick the correct door, Monty will show you a door with a goat. But after Monty has eliminated one of the doors for you, you obviously do not improve your chances of winning to better than 1/3 by sticking with your original choice. If you now switch doors, however, there is a 2/3 chance you will win the car. Counterintuitive though it seems. Winning rate. Suppose your strategy is stay. Left the car is behind door 1, you win. It doesn't matter which of the other doors Monty opened, because you're not switching to either. If the car is behind door 2, you lose. If the car is behind door 3, you lose. So the odds of winning with the stay strategy are 1 in 3. Now, suppose your strategy is switch, right column. If the car is behind door 1, you lose. If the car is behind door 2, Monty would have opened door 3, so you would switch to door 2 and win. If the car is behind door 3, he would have opened door 2, so you would switch to door 3 and win. The odds of winning with the switch strategy are 2 in 3, double the odds of staying. That's it. We already get an answer to the question, what is the Monty Hall Paradox? If you have any questions or suggest some topic, please leave a comment. We read all the comments of your guys. Introduce? The golden age of TV game shows. Let's Make a Deal was a real Monty
gem,
Hall,
wasn't it?
The maestro of surprises. Became famous not just for his hosting skills, but also for sparking a whole new kind of dilemma in probability theory. Picture this. You're on the show, facing 3 doors. Behind one, a shiny new car awaits, while behind the others lurk goats. Yep, goats. You pick door 1, hopeful and trembling with anticipation. Then, in classic Monty style, he swings open door 3, revealing yet another bleeding goat. Now, here comes the twist. Do you stick with your gut or take a wild swing and switch to the unopened door? It's like a math problem meets a guessing game meets a farmyard fiasco. So what's your move, contestant extraordinaire? Possible outcomes. To tackle Monty Hall problem math in a more humorous way, instead of laboriously counting which option leads to the car if you stick or switch, we could easily compile a chart for this. Let's say you pick door number 1. Without loss of generality, then the outcomes can be described as follows. Sure thing, sometimes it goes like this. In 2 out of 3 cases, you win the car by changing your selection after one of the doors is revealed. This is because there is a greater probability that you choose a door with a goat behind it in the first go, and then Monty is guaranteed to reveal that one of the other doors has a goat behind it. Hence, by changing your option, you double your probability of winning. Another way of seeing the same set of options is by drawing it out as a decision tree, as in the following image. Using Bayes' theorem, the Monty Hall problem math is like a mind-bending magic trick that leaves everyone scratching their heads. First off, why does the math play tricks on us? Why does sticking to your first choice feel like betting on a 1-legged horse in a 3-legged race, while switching doors suddenly turns you into the odds-on favorite? And then there's the randomness of it all. If Monty's just randomly flaunting goats, shouldn't our odds be as scrambled as a Rubik's Cube in a hurricane? Enter Bayes' theorem, the Sherlock Holmes of probability theory. It's like having a mathematical Watson guiding us through this bewildering maze. With Bayes at the helm, we can decode the Monty Hall conundrum like a seasoned cryptographer decrypting ancient scrolls. It's all about updating our bets based on the evidence, turning what seems like a game of chance into a strategic game of cat and mouse. So next time you're faced with Monty and his tricky doors, just remember, Bayes has got your back, turning goats into gold with the flick of a formula. Let H be the hypothesis, door 1 has a car behind it, and E be the evidence that Monty has revealed a door with a goat behind it. Then the problem can be restated as calculating PHE, the conditional probability of H given E. Since every door either has a car or a goat behind it, the hypothesis, not H, is the same as door 1 has a goat behind it. In this case, Bayes' theorem states that the problem as stated says that Monty Hall deliberately shows you a door that has a goat behind it. Breaking down each of the components of this equation, we have the following. PH is the prior probability that door 1 has a car behind it without knowing about the door that Monty reveals. This is 1/3. P note H is the probability that we did not pick the door with the car behind it, since the door either has the car behind it or not. PEH is the probability that Monty shows a door with a goat behind it, given that there is a car behind door 1. Since Monty always shows a door with a goat, this is equal to 1. PE not H is the probability that Monty shows the goat, given that there is a goat behind door 1. Again, since Monty always shows a door with a goat, this is equal to 1. Combining all of this information gives the probability that the car is behind door 1 is completely unchanged by the evidence. However, since the car can only either be behind door 1 or behind the door Monty didn't reveal, the probability it is behind the door that is not revealed is 2/3. Therefore, switching is twice as likely to get you the car as staying. Variant, the random Monty Hall problem. This result depends crucially on the fact that Monty was always guaranteed to open a door with a goat behind it, regardless of what door you picked initially. That is, PIH, PI not H. Now consider what would happen if Monty randomly opened a door we did not pick and it contained a goat. What is the probability that our first pick is correct, regardless of which specific door we picked? In this case, PEH, the probability that Monty will show us a door with a goat behind it, given that our first pick was correct and does have a car behind it, is still 1. If you pick the door with the car, the 2 other doors are guaranteed to have a goat, but PERI changes. This represents the probability that Monty picks a door with a goat behind it, given that your original choice of door had a goat behind it. In this case, Monty chooses randomly between one door that has a goat behind it and one door that doesn't have a goat behind it. Therefore, the probability that he picks a door with a goat is P not H1F. Laying this out, we get there is a 1/2 or 50% chance of our first pick being correct when Monty randomly opens a door and it happens to have a goat behind it. The naive reasoning that fooled so many mathematicians works in this case. That's it. We already explained Monty Hall problem math. If you have any questions or suggest some topic, please leave a comment. We read all the comments of your guys. Thank you for watching until now. Like, subscribe, and turn the bell button to get notices when we release new videos. Goodbye.